Monotonic Reads. Our second example of an anomaly that can occur when reading from asynchronous followers is that it's possible for a user to see things moving backward in time. This can happen if a user makes several reads from different replicas. For example, Figure 5-4 shows user 2345 making the same query twice, first to a follower with little lag, then to a follower with greater lag. This scenario is quite likely if the user refreshes a web page, and each request is routed to a random server. The first query returns a comment that was recently added by user 1234, but the second query doesn't return anything because the lagging follower has not yet picked up that write. In effect, the second query is observing the system at an earlier point in time than the first query. This wouldn't be so bad if the first query hadn't returned anything, because user 2345 probably wouldn't know that user 1234 had recently added a comment. However, it's very confusing for user 2345 if they first see user 1234 comment appear, and then see it disappear again. Figure 5-4. A user first reads from a fresh replica, then from a stale replica. Time appears to go backward. To prevent this anomaly, we need monotonic reads. Monotonic reads is a guarantee that this kind of anomaly does not happen. It's a lesser guarantee than strong consistency, but a stronger guarantee than eventual consistency. When you read data, you may see an old value. Monotonic reads only means that if one user makes several reads in sequence, they will not see time go backward, i.e. they will not read older data after having previously read newer data. One way of achieving monotonic reads is to make sure that each user always makes their reads from the same replica. Different users can read from different replicas. For example, the replica can be chosen based on a hash of the user ID, rather than randomly. However, if that replica fails, the user's queries will need to be rerouted to another replica. Consistent prefix reads. Our third example of replication lag anomalies concerns violation of causality. Imagine the following short dialogue between Mr. Poons and Mrs. Cake. Mr. Poons: how far into the future can you see? Mrs. Cake. Mrs. Cake: about 10 seconds usually. Mr. Poons: there is a causal dependency between those two sentences. Mrs. Cake heard Mr. Poons's question and answered it. Now, imagine a third person is listening to this conversation through followers. The things said by Mrs. Cake go through a follower with little lag, but the things said by Mr. Poons have a longer replication lag. See Figure 5-5. This observer would hear the following. Mrs. Cake: about 10 seconds usually. Mr. Poons: Mr. Poons: how far into the future can you see? Mrs. Cake? To the observer it looks as though Mrs. Cake is answering the question before Mr. Poons has even asked it. Such psychic powers are impressive, but very confusing. Figure 5-5. If some partitions are replicated slower than others, an observer may see the answer before they see the question. Preventing this kind of anomaly requires another type of guarantee. Consistent prefix reads. This guarantee says that if a sequence of writes happens in a certain order, then anyone reading those writes will see them appear in the same order. This is a particular problem in partition-sharded databases, which we will discuss in Chapter 6. If the database always applies writes in the same order, reads always see a consistent prefix, so this anomaly cannot happen. However, in many distributed databases, different partitions operate independently, so there is no global ordering of writes. When a user reads from the database, they may see some parts of the database in an older state and some in a newer state. One solution is to make sure that any writes that are causally related to each other are written to the same partition, but in some applications that cannot be done efficiently. There are also algorithms that explicitly keep track of causal dependencies, a topic that we will return to in the happens before relationship and concurrency on page 186. Solutions for replication lag. When working with an eventually consistent system, it is worth thinking about how the application behaves if the replication lag increases to several minutes or even hours. If the answer is no problem, that's great. However, if the result is a bad experience for users, it's important to design the system to provide a stronger guarantee, such as read after write. Pretending that replication is synchronous, when in fact it is asynchronous, is a recipe for problems down the line. As discussed earlier, there are ways in which an application can provide a stronger guarantee than the underlying database, for example, by performing certain kinds of reads on the leader. However, dealing with these issues in application code is complex and easy to get wrong. It would be better if application developers didn't have to worry about subtle replication issues and could just trust their databases to do the right thing. This is why transactions exist. They are a way for a database to provide stronger guarantees so that the application can be simpler. Single-node transactions have existed for a long time. However, in the move to distributed, replicated, and partitioned databases, many systems have abandoned them, claiming that transactions are too expensive in terms of performance and availability, and asserting that eventual consistency is inevitable in a scalable system. There is some truth in that statement, but it is overly simplistic, and we will develop a more nuanced view over the course of the rest of this book. We will return to the topic of transactions in chapters 7 and 9, and we will discuss some alternative mechanisms in part III 4. If the database is partitioned, see chapter 6, each partition has one leader. Different partitions may have their leaders on different nodes, but each partition must nevertheless have one leader node. Multi-leader replication. So far in this chapter we have only considered replication architectures using a single leader. Although that is a common approach, there are interesting alternatives. Leader-based replication has one major downside: there is only one leader, and all writes must go through it. IV If you can't connect to the leader for any reason, for example due to a network interruption between you and the leader, you can't write to the database. A natural extension of the leader-based replication model is to allow more than one node to accept writes. Replication still happens in the same way. Each node that processes a write must forward that data change to all the other nodes. We call this a multi-leader configuration, also known as master-master or active/active replication. In this setup, each leader simultaneously acts as a follower to the other leaders. Use cases for multi-leader replication. It rarely makes sense to use a multi-leader setup within a single data center, because the benefits rarely outweigh the added complexity. However, there are some situations in which this configuration is reasonable. Imagine you have a database with replicas in several different data centers, perhaps so that you can tolerate failure of an entire data center, or perhaps in order to be closer to your users. With a normal leader-based replication setup, the leader has to be in one of the data centers, and all writes must go through that data center. In a multi-leader configuration, you can have a leader in each data center. Figure 5-6 shows what this architecture might look like. Within each data center, regular leader follower replication is used. Between data centers, each data center's leader replicates its changes to the leaders in other data centers. Figure 5-6. Multi-leader replication across multiple data centers. Let's compare how the single leader and multi-leader configurations fare in a multi-data center deployment. Performance in a single leader configuration. Every write must go over the internet to the data center with a leader. This can add significant latency to writes and might contravene the purpose of having multiple data centers in the first place. In a multi-leader configuration, every write can be processed in the local data center and is replicated asynchronously to the other data centers. Thus, the inter-data center network delay is hidden from users, which means the perceived performance may be better. Tolerance of data center outages in a single leader configuration. If the data center with a leader fails, failover can promote a follower in another data center to be leader. In a multi-leader configuration, each data center can continue operating independently of the others, and replication catches up when the failed data center comes back online. Tolerance of network problems. Traffic between data centers usually goes over the public internet, which may be less reliable than the local network within a data center. A single leader configuration is very sensitive to problems in this inter-data center link, because writes are made synchronously over this link. A multi-leader configuration with asynchronous replication can usually tolerate network problems better. A temporary network interruption does not prevent writes being processed. Some databases support multi-leader configurations by default, but it is also often implemented with external tools, such as Tungsten Replicator for MySQL, BDR for PostgreSQL, and Golden Gate for Oracle. Although multi-leader replication has advantages, it also has a big downside. The same data may be concurrently modified in two different data centers, and those write conflicts must be resolved, indicated as conflict resolution in Figure 5-6. We will discuss this issue in handling write conflicts on page 171. As multi-leader replication is a somewhat retrofitted feature in many databases, there are often subtle configuration pitfalls and surprising interactions with other database features. For example, auto-incrementing keys, triggers, and integrity constraints can be problematic. For this reason, multi-leader replication is often considered dangerous territory that should be avoided if possible. Another situation in which multi-leader replication is appropriate is if you have an application that needs to continue to work while it is disconnected from the internet. For example, Consider the calendar apps on your mobile phone, your laptop, and other devices. You need to be able to see your meetings, make read requests, and enter new meetings, make write requests at any time, regardless of whether your device currently has an internet connection. If you make any changes while you are offline, they need to be synced with the server and your other devices when the device is next online. In this case, every device has a local database that acts as a leader. It accepts write requests, and there is an asynchronous multi-leader replication process sync between the replicas of your calendar on all of your devices. The replication lag may be hours or even days, depending on when you have internet access available. From an architectural point of view, this setup is essentially the same as multi-leader replication between data centers. Taken to the extreme, each device is a data center, and the network connection between them is extremely unreliable. As the rich history of broken calendar sync implementations demonstrates, multi-leader replication is a tricky thing to get right. There are tools that aim to make this kind of multi-leader configuration easier. For example, CouchDB is designed for this mode of operation. Real-time collaborative editing applications allow several people to edit a document simultaneously. For example, Etherpad and Google Docs allow multiple people to concurrently edit a text document or spreadsheet. The algorithm is briefly discussed in Automatic Conflict Resolution on page 174. We don't usually think of collaborative editing as a database replication problem, but it has a lot in common with the previously mentioned offline editing use case. When one user edits a document, the changes are instantly applied to their local replica, the state of the document in their web browser or client application, and asynchronously replicated to the server and any other users who are editing the same document. If you want to guarantee that there will be no editing conflicts, the application must obtain a lock on the document before a user can edit it. If another user wants to edit the same document, they first have to wait until the first user has committed their changes and release the lock. This collaboration model is equivalent to single leader replication with transactions on the leader. However, for faster collaboration, you may want to make the unit of change very small, for example a single keystroke, and avoid locking. This approach allows multiple users to edit simultaneously, but it also brings all the challenges of multi-leader replication, including requiring conflict resolution.